Hello, everyone. My name's Lucas Henneman. I'm an assistant professor at George Mason University in Fairfax, Virginia. I'm going to be telling you about work that I've been doing with a really great team looking at spatial temporal trends in 4 decades of United States on-road air pollution. Now, my team for this project is made up of some really impressive people at Georgia Tech, UT Austin. I'd also like to acknowledge Christian Hogreth at EPA, and this is all part of work that's in review primarily it's been funded by the Harvard MIT Air Climate and Energy Center. All right, so we're motivated by traffic-related air pollution, or TRAP. So I've listed some of the main ones here: NO2, NOx, CO, EC, often PM gets thrown into this mix. I've highlighted NO2 and CO because those are the two that I'm going to focus on today. And TRAP gets talked about a lot in epidemiological research, environmental justice research, where exposure to these things has been linked to a range of negative health impacts and adverse societal outcomes. And often in these research domains, the exposure to these pollutants is approximated using some kind of proximity measure. So road proximity, for instance, for traps in particular. There's been a movement lately to move to some modeling, so chemical transport models like CMAS, or even satellite measures. And so this work is going to explore the ability for all of these things to measure TRAP and exposure to TRAP. And you know, we kind of benefit here looking at these in that TRAP concentrations have changed in time and space over recent decades. So it's led to some questions. First, how much information about the gradients in TRAP is contained in simply where roads are located? So these EPI and EJ studies have used road proximity. How much information is there? And just thinking schematically about this, you know, if you're driving along a road that's going in this direction, you know, you might assume that closest to the road or even on the road, you'd see the highest concentrations. These would sort of fall off as you got further and further away from the road. Now, in sort of another dimension across time, in 1980, vehicles were a lot more polluting than they are now. This distribution probably looked a lot different than it does 40 years later today. And so this research looks into both how these gradients looked back then and how they've changed over time. Then we have some nice long-term products of models of satellites. And you know, since these also are used in these exposure studies, we're curious too whether they, or how well they approximate the observations and the gradients in the observations that we see in this work here. And so that's where we've defined our metric called roadiness. And roadiness is a measure of road proximity. And it all starts with the USGS's road link network. So this is what the road network in Virginia looks like. You can see there are many, many links, and it's at a fine spatial resolution. On top of that network, which we don't just have in Virginia, but we have for every state in the United States, we overlay a fine grid. So we use 4 kilometers and sum the road lengths in each grid cell. We then define roadiness based on the inverse inverse distance weight of all of the road lengths in grid cells other than the grid cell of interest. So the roadiness in cell I, defined for this capital D, is the sum of all of the road lengths in all of the other cells, J, divided by the distance between cell I and cell J. Now that distance is a function of this capital D, and that capital D we've assigned digits from 1, 1.5, and 2, and I'll show you what that leads to in this figure. So just looking at road length on the left, if we just sum up the road length of all of the grid links, or all of the road links in the database, and plot their grid cell, it looks like this. So certainly some bright spots near cities. With a capital D of 1, we get a very diffuse surface here, and as you raise that capital D, you get stronger gradients between rural and urban areas. Just to note that since in calculating these, if we didn't scale them, they would be wildly different units. We've scaled these all to their z-score, so they all have mean 0, standard deviation of 1. And early testing of this metric showed us that all of these trap pollutants that we're looking at, so NOx, NO2, CO, and EC, all had the strongest relationships with a D of 2, so strongly correlated with inverse distance squared. So that's the results that I'll be presenting here. The data that's going into our analysis, so we have observations at that top row, monitors, all of the EPA AQS monitors from 1980 until now. Those have all 4 pollutants. CMAC will be looking at both 36 kilometer and 12 kilometer. Again, all 4 pollutants with some differences in the years available. So these are long-term simulations provided by the EPA. And then 3 different satellite measures. So OMI, a merged satellite project that comes from a merged satellite product that comes from GOM, GOM2, and Skiamaki, and then MOPIT for CO, which I actually won't present today, but that's in the final analysis. And again, they have some different coverages in their years. And so we can start just by plotting the trends for different, at monitor locations with different roadiness designations. So here I've just separated them into 3 categories, high, medium, and low. Looking at that top plot there for observed concentrations since 1980, you can see there's pretty high stratification between areas that have high roadiness, medium road proximity, and then low. And the models, so 12 kilometer and 36 kilometer CMAC, do a fairly good job of capturing that. So the high roadiness is definitely higher than the medium and low, and similar with 36 kilometer, although you start to get some similarities in the medium and low. And the satellites too, you get very nice stratification along their time spans. CO is a little bit different. So again, you see sort of large decreases across time, especially in the observation record going back 40 years. And at the beginning, it was pretty clear that areas with high road proximity had higher concentrations, although that difference has certainly shrunk in recent years. In the models, it seems like give a pretty similar answer here. The satellite, actually, we see very little difference. So that MOPIT product isn't giving us the stratification between areas with high CO and low. And we want to put some numbers to this. So we're using this hierarchical modeling framework. There's a lot of symbols in here I'll walk through in the next minute or so. So For concentrations at monitor locations K and time T, we have the following coefficients. So our beta naught is our average concentration at time T equals 0. Our beta R is the relationship between concentration and that S roadiness 2 metric, again at our time T equals 0. Beta 1 is the relationship between concentration and time, so the change per year in this case. Beta 2 is the concentration time interaction with S roadiness, so how that temporal trend has changed as you move closer and further away from roads. We include a term in here for meteorology, multiple terms in here for meteorology with interactions between all of the different meteorological terms. And we include this G. So here we've stratified this model a few different ways for the different results that I'll present. One of the ways that I'll show is stratifying by decade. Another way is stratifying by different state groups to look at differences in location. Two types of error here. So monitor specific random intercept we've included, and random measurement error as well. Okay, so NO2 over time. Looking at this first upper left panel here, these are our beta zeros. So these are our average NO2 concentrations at the beginning of each decade, 1980, 1990, 2000, 2010. You can see each one of those subsequent years, there's been a pretty steep decline in NO2. Similarly, as the time trend has been negative, so has the relationship between concentration and our roadiness metric, and that's weakened over time. So you can think of it as a general flattening of the surface as impacts of roadways have decreased on concentrations. Now, these so beta 1 is our change in NO2 over time. So there's an interesting story here where the first 2 decades, 1980 to 1999, that change per time was about -2 parts per billion per year, and it's similar to the change per time 2010 to 2019. The one difference being 2000 to 2009, and that's where there was a really big influence of other sources cutting their emissions. So think about the NOx budget program, for instance, cutting power plant emissions. See that really big drop off in NO2 concentrations. And this final panel here is the relationship between S roadiness and the time trend. So think about for every standard deviation increment you get closer, higher road proximity, it changes the temporal trend by this much. And that's stayed reasonably constant over the years. So NOx or road proximity is having a similar influence on the temporal trend over this entire period. CO looks similar, especially on the left here. So average CO decreased across decades. Average relationship between concentration and road proximity weakened across the years. The change per year has gone down drastically. So we're seeing change per year on average of 50 parts per billion less CO per year. These days, it's been around 5 parts per billion CO decrease per year. And similarly, the road proximity has had less and less influence on this temporal trend as we've come further on in time. So we use this approach to look at CMAS products. So, and the satellite products. So this is just for NOx, and this analysis was run just from 2002 to 2010 when we were evaluating all these products. We had all these products available. One thing to note is that these coefficients are presented as a percent of the mean from 2002 to 2010. And all of the models and metrics do a pretty good job of calculating that average concentration as a percent of the mean and average relationship with road proximity as a percent of the mean. You start to get differences in the, oh, and I'll note that even, these, both the 12 kilometer and 36 kilometer CMAC products do well for all of our regression coefficients here. You start to see differences in the satellite products though. So OMI is overly sensitive to this temporal trend and the impact of road proximity on the temporal trend. And both satellites are actually kind of overly sensitive to the road proximity influence on the temporal trend. And so that was in the model evaluation piece, but then we also applied this to a policy evaluation, and it centered around this question: how have trends varied in states that didn't adopt California's automobile rules? So EPA allows other states to opt into California's emissions rules. We are looking at 3 rules in particular, so light duty criteria pollutant, light duty greenhouse gas, and zero emissions vehicle rules. There were 11 states that opted in model year 2011 or before. They're listed here. And so we grouped all of the 48 states in the lower 48 into one of these groups. So we had California itself, we had yes states that adopted California state standards, and no states that stuck with the national standards. And we're looking 2010 and onward here. So NO2, first thing you notice, so average concentrations in 2010, the California and yes states had higher concentrations than the no states. So that sort of makes sense why the yes states would pursue these policies. But interestingly enough, so California had the highest relationship between concentrations and roadiness, but no states actually had a higher relationship between concentrations and roadiness than yes states, even though yes states were the ones that pursued these policies. And the average change per year, so was actually highest or most negative in California and yes states. So they did a reasonable job of controlling for NOx or improving their NO2 concentrations better than no states. But the temporal trend or interaction between the temporal trend and roadiness was highest in California, but similar again in yes and no states. So even though yes states concentrations were improving quickly, they weren't necessarily near roads, whereas they had, while they had implemented these standards. So I'm nearing time, so I'm gonna just put up these conclusions. Excited to discuss at the conference, and thanks again. See you all soon. Bye-bye.